Hey folks, welcome to this video on finite differences. Finite differences helps us with sequences that are polynomial in nature, so I'd like to show you a little bit about what they are and what they do. First of all, the finite difference by definition is the difference between the terms, and in this case you see there's a difference of 4 between the first two and 4 between the next two. And so that really makes us happy because that number is a constant 4. And in this case, it tells us that the sequence, if we call this a sub n, that sequence is going to be linear. And the neat part about it is this 4 tells us what the coefficient of the n term is going to be. And the last thing we need to do is figure out if the first term is a sub 1 and that number is 3, then how would we achieve a 3 if we plug a 1 in for this n? So in this case, we'd have to subtract 1. So essentially, we can narrow down a linear or arithmetic sequence very quickly by simply doing a quick finite difference computation. Very easy to do. For example, if you had something like 5, 8, 11, dot, dot, dot. This is going to be 3. That's going to be 3. So we know that a sub n is going to be 3n, and then we've got to get this 5, so we would add 2. So you can see how quickly you can do that with finite differences. So let's go one step deeper in this one. Let's take a look at a quadratic sequence. In this case, we'd like to list out what the terms are. So let's try this one with p sub 1. In this case, if I plug in a 1 for n excuse me, n, I would get 4 minus 6 plus 5, which in this case comes out to be 3. And then p sub 2 is going to be plugging in a 2 for n, which is going to end up being 16 minus 12 plus 5. All right, and in that case, I'm going to get a 9. P3, I'll just do a couple more of these. That's 36 minus 18 plus 5, or 23. And one more just for fun here. 4 is going to be 64 minus 24 plus 5, or in this case, 45. All right, now let's work out the finite differences for these terms. This is the first four terms of the sequence. So we know that the difference between 3 and 9 is going to be 6. The difference between 9 and 23 is going to be 14. And the difference between 23 and 45 is 22. Excuse me. So notice that in this particular case, there is no pattern in the first set of finite differences. But if you go one step further, in other words, to the next layer, we notice that this is plus 8 and this is plus 8. Oh gosh, look at that. So that's interesting that we end up with a constant, which means that this row must have been linear. And of course, this row here is constant, and then this original row was quadratic. So it seems to go up in polynomial power, or in a power of the value. So each layer is a power, essentially. Well, let's move on and see how that summarizes. What we're going to do is we're going to pretend that we don't know what the A, B, and C are. And we're going to work through the first few numbers. So obviously here n is equal to 1 in p sub n. So we'll do this. First one is going to just give us an A plus a B plus a C. P sub 2 is going to be 4A plus 2B plus C. P sub 3 is going to be 9A plus 3B plus C. And then we'll just do again the fourth one. Obviously we could go on for a while, but 16A plus 4B plus C. And finding the first layer of finite differences, we know it's not going to be constant. But if we subtract upward, we end up with 3a, and then 2b minus b is just plus b, and the c's drop out. And in the second case, right over here, we end up with 5a plus b again, and then this turns out to be 7a plus b. And our second layer gives us just 2a. 2a. So what's interesting about that is when you look at this top row over here, these three interesting expressions give us the coefficients of a, b, and c. So if we go backwards, let's this 2a right here. Let's go back to the last screen. that 8 is representing 2a, therefore a equals 4, and that certainly checks out. And once we found the a value, we could work to the next part and the next part. So this 6 would equal the 3a plus b. And if you're wondering where I'm getting 3a plus b from, I'm just getting it from right here. This is 3a plus b every time. So that's going to be 3a plus b, which is located here. And we've already found the a value to be 4. So that would be 12 plus b is 6. And so b equals -6. And that also checks out above right here. And obviously then we can go back to the beginning, this number 3, and set it equal to a plus b plus c and solve that as well. So knowing that, now that we know that these have a special situation, we can try it for a problem like this one, where the 1, 3, 7, 13, 21 is going to be worked out for us. So 1, 3, 7, 13, and 21. We're just going to do a few of these because we only need a couple of layers. Actually, we only need to verify that it is quadratic. Excuse me, let me take this one out. So 1 and 3 makes a 2 is the difference there, 4 is the difference there, 6 is the difference here, and then we end up with 2 and 2. We are only concerned about two things. First of all, that this is constant, because that being constant helps us to know that it is quadratic in nature. And then we're going to just pluck out these three terms. So we'll start with the one on the far right. The number 2 is equal to 2a. The second term, that's this guy right here. The second one is also a 2. That 2 is equal to 3a plus b. And this number 1 from right over here is equal to a plus b plus c. Now this side of the equation will always be the same for a quadratic. The first term will be the 2a, then the 3a plus b, and then the a plus b plus c. So we can see right away that a is equal to 1. If we plug a 1 in right over here and then bring that 3 to the other side, b is equal to -1. They cancel out here. The c is also equal to a 1. And so this time our p sub n is equal to just n squared minus n plus 1. And that's the answer for the actual nth term for this sequence. So oftentimes it's written this way, n squared minus n plus 1 in a parentheses like as the nth term. So we can kind of see what that thing looks like. So there's a good summary of how finite differences can be used to find a quadratic nth term. Notice the quadratic nth term p sub n right down here at the end. So the thing I like about it is it's actually very quick, and of course you have to memorize these three items, but you can generate them very quickly using the arbitrary case. All right, that summarizes the first video of two videos. Next we'll move on to the next layer, which is cubic sequences.